Okay, so I was thinking about the way that I explained the AC power issues on Wednesday last week. So I didn't do a good job on Wednesday. So I spent some time to summarize all the different equations and the concepts onto these papers. So once again, it looks super confusing. It's like the phasors and what else concept I introduced previously. If you understand my summarized problems, you should be able to cover 90% of the problems. You'll be able to understand pretty much everything. So it's just these couple papers over here, okay? I don't want to directly just throw all these equations to the paper and eventually it's getting you extremely confused. Because you will see people, some of the people are doing, for example, our tutorials are using the phase angle over there. I know you don't know what I'm talking about, but so they use VRMs, IRMS, and phase angle to get the average power. But eventually, if you look at some other instruction materials, it totally use a different method. It use like I square R or something. Like why both different methods are getting the same answers. So today I'm trying to explain that to you. Okay, I was trying to find out the best way to explain this. I watched several videos, some of the really highly rating teachers on YouTube, how they explain this concept, but none of them did the same thing like what I did on the paper. So I think this solves a lot of problems because I just put all the cases into two different models. And if you can solve these two models, you'll be fine, okay? So first, why do we care about AC power? If it's a DC power, right, you got a V here, I here, it's super simple. So power equals VI, right? However, for a AC source, if you got a resistive load, you got voltage in, right? This is voltage. So divided by R, so V divided by R, so I's, sometimes you'll see amplitude. It's the same stuff, amplitude. Sometimes you'll see a term magnitude. Or sometimes you'll see a modulus. Did I spell this correctly? So there are same stuff over here. So you can see if V has a VM, has a magnitude, which is the max value of the V, divided by R is the resistive load, so the I will be lower, right? Value-wise. Oh, depends actually. But anyway, let's just assume that the I will be lower. Okay. Are they in phase? Is the current voltage in phase? Means they have the same phase or no? Yes, it's just a resistive load. It's not shifting the phase at all. So you could use dots of the V and I's. So V times I is giving the power, right? No problem, no phase shift. However, if you have a load looks like this, it could be a Z, it can be capacitive or inductive load. Eventually, your V looks like this, but I becomes this. So how do we calculate the power? Yeah, there's phase shift, right? This is time. How do you figure out the power calculation problem? So electrical engineers have to figure out a way, right? What's that?
Could you shift one of the equations so they
Yeah, that's eventually how you calculate. It's called average power or reactive power. Eventually, there are two ways to calculate it. But now, yeah, this is how the electrical engineers came out as a solution to characterize the power consumption of the AC power system, right? But for this one, if you just look at time, because time is the dimension of this physical world. Okay. So at this moment, it has a certain current and certain voltage. This is I. So it does have a power consumption at the moment. If you treat these plots as discrete points. You agree with me? With a super short time frame, there will be a current value and voltage value over there, and voltage times I will definitely give you a power. So what's the name of that power? You'll see this term in your homework assignments. probably twice. I think 2 of the problems are giving you that concept, but can be confusing. So what is that called? So the name explains itself. It's called instantaneous power. All right, and the way to calculate it is what's the name of the power though? I mean, there's a letter. Okay, let's just say P. If you plot this instantaneous power, you can see these. This is the low. Getting lower, and at some point it's gonna reach a peak. I think I have a curve here to show you. Do I? Well, I didn't bring it. Oh, I have it here. Okay, so seems like here it's reaching a peak, right? So eventually, for example, it's reaching negative power here, but getting peak. And this has become the lowest. My brain is not a computer. I couldn't resolve it. But anyway, you can tell probably here is reaching a peak. Okay, so there will be a P max. Oh, another question: why we are getting a negative power here? How is that possible? So resistor is not able to generate a negative power because resistors is always consuming power. It's generating heat.
Is it based on the direction of the power swing?
Yes. So the thing is, whenever you have reactance, or it could be a inductive load or capacitive load, it's actually storing the energy and send it back to the source. So it's not consuming power, but it just store it temporarily and send it back and forth. So when we derive the equations, you will figure out why mathematically. But now, just let you know, like why we have negative power is because it's storing power over there. It's not consuming, but eventually send it back. But at least you know that there will be a max power calculation. There's a minimum power from the instantaneous power in the curve, and you can calculate. And I don't think it's going to require you how to derive it. Eventually, it's giving you that conclusion here to calculate it. And we use these numbers really very rarely, so I think we just need to know how to calculate it. For that, 1 out of maybe 10 or 15 problems from the homework. That's for instantaneous power. And what are these? That's the important part of it. That's the things we really care about. P is called average power or real power. We'll spend probably 80% of the time in this lecture to talk about that. There are 2 different ways to calculate it, and can confuse you a lot. And so this one is called reactive power. They are calculated in the same way, but the thing is, if we spend 80% time here, it's a very similar way to calculate Qs as well. So we just need to spend most of the time over here, right? Why do we care about average power? Because it's all changing and there's a phase shift. So we just want to figure out a way to characterize the power consumption of the system. Instantaneous power is only giving you the power at this time point, right? Sometimes it's meaningful. We probably want to care about it, but eventually, overall, we just want to care about the overall power consumption using this time varying signal. The DC is easy, just V times I. But for here, we just have to get the average voltage and current to find out the average power consumption from these peak voltages and currents. So that's the goal, right? The goal to find out this is to characterize the power consumption of the source and the load. That's it. That's why we spend all the time today and probably the rest of the week, and also why we are doing homework 10, right? Okay, so how do we characterize that? Because it's always changing, right? We want to find a way or find a voltage can represent this change or this signal. Here's a really good plot. I'm showing you here. Doesn't matter if there's a phase shift or not, but eventually it looks like this. Okay, so if this is a voltage, for example, this is the voltage, this is current. No phase shift, it's a resistive load. Okay, I can plot the power, just time V times I. V times I, the power is changing as well. Okay, so what is the average power? What's the average power? Sometimes it goes up, sometimes it goes down, right? Seems like the average power is in the middle. Why? You look at this plot. It's splitting this top part into two pieces here as well, and you rotate and fit in here. Okay, same thing for these two pieces. You fit in here. Okay, and this piece fitting here. It's going to be the same area as half of this region. You know what I mean? If you draw a half of the power, the peak power, and draw a line here, the rectangular shape has the same area as the two bumps. Make sense? So if you still want to use the V times I, just make it simple, just V times I. You cannot use it here because it's always changing, right? So we want to find out the value for V and I that is able to we can directly use that V and I, the multiplication, to find out the power, and we can call it average power. So what are these V and I's called? It's called root mean square, or VRMS, or IRMS. So if you see our AC system is 120 volts at 60 hertz, 60 hertz of the outlet over there, right? So if you probe it, so we're getting 120 volts and 60 hertz. But this is a VRMS value. It's not the peak value. It's a sine wave, right? So this peak is not 120 volts. It's something else. So VRMS is calculated as, it's not derived that way, but the thing is, let's just split that way. So it's V power equals V peak, okay? Peak power divided by 2 equals V peak times I peak divided by square root of 2. There's a longer way to derive it, but we're not doing that. Let's just simply split it, okay? So Vm, which is the magnitude, peak. So eventually this is giving us what? Vm times Im will be peak power. Square root of 2 times square root of 2 is 2, right? So they're equal. So this is called VRMS. This is called IRMS. So in that case, we can use VRMS times RMS to calculate the average power of this sine wave.
Since the voltage and the current can go negative, is the VM or the RMS the difference between the lowest and the highest voltage, or is it just the distance from the highest of
It's
the y-axis and
yeah.
zero?
Yeah, I think this is a resistive load. It's just labeling this in the middle, but actually the voltage is, I don't think it's able to go negative. It's just a resistive load. Or it's just a reference, right? We're just looking at the reference. There's no negative power for the resistive load, but you are asking for something else like reactive load. So for reactive load, a reactive load doesn't have any real power consumption. Only resistive load have real power consumption. It stores the energy and eventually send it back. So it's not consuming energy. Only if we draw a circuit like this, for example. I know you are wondering why a resistive load doesn't consume energy, right? It's designed that way. I mean, whoever designed it, manufacturer, designed it that way. So it's not consuming energy. It stores the energy, and whenever you get a negative potential over for the source compared to the load, it sends it back. So it's not consuming anything. Only the resistive load in the cable, in the line, transmission line, or any of the real resistance in the load, they generate heat and consume energy. Okay? All right? Let's see. So we need to calculate P and Q. So P is average power, or it's called real power. Q is called reactive power. They both come from the complex power term, but we'll talk about that later. But now let's just focus on the average power and reactive power. So keep in mind, average power and real power is from the resistive load, and reactive power is from the reactive load. Could be inductance or capacitance. They're separate. But the problem is a lot of times you have both resistive load and capacitive load or inductive load in the same time, in the same circuit, and you got a voltage as a only source supplying voltage. You have to calculate current, and eventually how do you separate that real and imaginary parts to find out the average power and reactive power. That's a challenge for this week and the homework assignment. That's all we are going to do. That's why we are here, right? Let's get into it. Okay. For example, this one, okay? I'm not giving you numbers. Because this is going to cover all these cases in general. If this guy has a Vg cosine omega t, okay, that could be fine. This covers all the cases. Why? Because I'm just using the voltage phase as a baseline, so it's zero phase shift. I don't have a plus theta or plus phi or anything, right? No phase shift, which is fine because for two signals, for example, the current and voltage, if I use the voltage as the reference, you just shift your current accordingly to the same direction. So I could have this one have no phase shift. It just compared to the voltage, your current will have a certain phase shift, depending on the load, right? I know it's confusing. So this is R. This is I want to use A and BJ, for example, because it's A plus BJ, okay? A plus BJ. Remember before we do this from last week, even during the problems in the second midterm, right? So we're still doing like V over A plus BJ to get a complex current, remember? That's why it's getting confusing, because this week we're totally dealing with it in a different way, okay? So this is still valid. So that's why I want to show you, if you use this traditional method, how to calculate the average and average or real power and reactive power as well. So first, let's say so the method one, always remember this, okay? So method one is you can focus on the resistor itself. Keep in mind, it's really important. I summarized everything just to this conclusion. So method one, you just focus on the resistor, because only the resistor is consuming real power, like I said, by definition, okay? That's the definition of the real power. Real or average power, the same thing, okay? Just see different terms. Real or average power. Because only the resistor is consuming real or average power, okay? So if we just look at the resistor, if we can get a voltage here and the current here, and we're done. And we know that the voltage and current for the resistor is in phase. We don't even need to worry about the phase shift between current and voltage. We just need to find out the RMS values of the voltage and current, and then we are done. Does that make sense? So let's come back to this point. It will all come together, trust me. It's not difficult. So electrical engineers eventually find out a way to characterize the power system, power consumptions. That makes sense, right? How do we do that? Using RMS values. Okay? So we can use RMS values to calculate the power of the AC power system. How do we get RMS values? Super simple. The peak value divided by square root of 2. That's it. Okay? Good here? All right. Now, it's given that resistors are the only components consuming average power in the circuit. If it's asking you to calculate the average power of this circuit or the average power delivered by the source, is the same thing because it's only source delivering power, right? So the average power in the circuit is only consumed by the resistor. So in that case, okay, to find out the average power, we just need to find out the RMS V and RMS I of the resistor. That's method 1. Just look at the resistor. Don't look at the rest of the circuit. RMS V or VRMS and RMS. Then just VRMS times RMS. So P of the resistor is, what is the VRMS over here? So peak voltage divided by square root of 2, right? So what's the peak voltage? So it's gonna be Vg over the magnitude of the resistive load, A squared plus B squared times A. That will be the voltage across it. How do we get there? So this is the sine wave, right? This is the sine wave. So it's gonna send that sine wave to the circuits as well. But because you have this component, so the voltage will be the voltage of this of here and here will have a phase shift compared to this guy, right? But the magnitude-wise, we can use the voltage divider based on the voltage divider theory to find out the voltage drop over this resistor. Is there a better way to calculate it? Because the resistive load is A plus Bj, and the magnitude of the resistance is A squared plus B squared, and square root of it. And eventually the magnitude of this guy is A. The modulus of this resistor is A. So times A will be the voltage across it. Let's do this. Let's slow it down a little bit. So Vg is the peak voltage, right? Vg is the peak voltage. It's going to be a cosine wave here, like this. So this is Vg. So Vg divided by square root of 2 is giving you what? VRMS of this source is Vg over square root of 2. Okay? And the magnitude of the resistance is this. So this divided by this is what? This is the VRMS. This is a square. This is the magnitude of the resistance. So this is giving you what? IRMS. So this VRMS is the VRMS of the whole thing, right? That's the peak V. That's the VRMS here. Okay. So you need to find out the VRMS of the across the resistor. What is it? So it's going to be Vg over square root of 2. That's the VRMS here, right? Divided by the whole resistance, which is A squared plus B, A squared plus B squared, and times the magnitude of A. Okay, so that will be the VRMS are the resistors RMS. I know it's confusing, but keep in mind, when you are calculating RMS, you always want to divide it by the resistance magnitude. So, because V and I, it's just Ohm's law, right? So convert from V to I to V. But for RMS domain, you always use the magnitude of the resistance. Keep that in mind. If you have a complex resistance or impedance, you use this to find out the modulus of or magnitude of the resistance of the impedance. So VRMS converted to IRMS, you need to divide VRMS by the magnitude of the impedance, which is this, and times the resistance share. It's like a voltage divider. This is the resistance share over here. We can consider this is the IRMS, right? And times the resistance, you're getting the voltage. Make sense? All right. For different circuits, it's still the same theory. So it's pretty much everything. Okay? Just basically amplitudes. Okay? So amplitudes of the impedance times RMSI, you get the RMSV. Same thing. You divide your VRMS by the impedance magnitude, you get the IRMS. Okay, just keep doing this for the whole problem assignments. All right, so how do we get the power, average power for the resistor? There's no phase shift, they're in phase. So it's basically just VRMS times I, oh, I didn't label it, but the same I everywhere, right? That equals VG over, oh, this is gone, A squared plus B squared times 2 and times A. Is that correct? Let me compare with my notes, see if that's correct. VG squared, yes. That's right, thank you. So this times this, right? This may look weird because I didn't plug in numbers into it, but this covers all the cases. Let me double check here really quick. Yes, that's right. Okay. So this covers the case that you have this one and two components in series. That's method 1. What about method 2? So remember, what is method 1? Focus on the resistor, right? Method 2. Use the overall impedance. So you'll see this a lot, especially in the tutorials and homework assignments. So they are telling you that P equals Vm times Am 2 cosine theta V minus theta I, but didn't tell you where this comes from. Right, so if you just follow the tutorial, that's why I think I'm useful. If that's the case, I'm not adding too much more to you guys, but helping a little bit, right? If you just follow the tutorial, you'll just keep using this equation from the beginning to the end, because this is what it tells you. And eventually, it gives you the same result, which is really magical. Okay, and also fun, you know. So what is this? Vm over 2 is what? So it's basically Vm over square root of 2 and Am over square root of 2, right? Cosine theta V minus theta I. because this is basically VRMS times IRMS cosine theta V minus theta I. Because this is what the tutorial tells us, so we are wondering, can we use the same method for this problem and to reach the same answer? Is that possible? It should, right? But how do we do that? So it's asking for the average power of the whole circuit. Again, so for the first method, we didn't care about the inductive load because we know that the resistor is the only component consuming average power. Okay, so the whole focus was find out the VRMS of the resistor, find out IRMS of the resistor. Okay, and this is still valid for this calculation. Why? What's the phase shift of the resistor in terms of V and I? What's the angle difference between V and I for the resistor? 0. So what is cosine 0? What's cosine 0? Right? Right? Cosine here, like almost 0, okay? So these two lengths are the same. So cosine 0 is what? 1. So do we care about this? No, but the equation is still valid, remember? Since we didn't times that at all. We didn't even care about that cosine term at all. Does that make sense? It all comes back soon. Trust me. So now it's still confusing, but all comes back to this point. Did we use the equation, the theoretical or classic equation over here? VRMS times RMS times cosine, this one? No. For the resistor, no, because that cosine term is 1. And when we only focus on the resistor, we get a VRMS and RMS. Just feel free to do the multiplications, then you are done. Because there's no phase shift. Both voltage and current are in phase. However, because this is asking you for the source, how much average power is being delivered by the source. So if you are looking at the whole circuit, when we have this impedance involved, the voltage and current are not in phase anymore. Does that make sense? If you just look at the voltage here and the current here, the overall current and overall voltage are not in phase. Do you agree with me? Because the current here, remember the problem we did in exam 2, right? You have to use the voltage divided by the impedance to get the current, right? You're having a complex part over here, so there's no way that these two will be in phase. So the voltage and current are not in phase. For the overall voltage and overall current are not in phase. But however, just look at the resistor, the voltage and current are in phase. Okay, now let's come back. When we just focus on the resistor, voltage and current in phase, that's why we can ignore that cosine term. Okay? Now, we are looking at the whole circuit. This is the overall current, this is the overall voltage. And they are not in phase anymore. This is not 1 anymore. You agree with me? Okay, good. Now let's see if we can get the same answer. What is VRMS? Since we have VG in here, right? So feel free to have VG in there. It's not a big deal. So VRMS what? VG over what? Square root of 2 by definition. What is IRMS? What is it? IRMS. Oh, so the way, remember I told you guys, the way to convert back and forth between VRMS and IRMS is to use impedance magnitude. Keep that in mind. Okay, that covers 80% of the problems. So in that case, how to convert it? How to convert the yeah, it's going to be VG over square root 2, right? That's the VRMS divided by, since we learned this before exam 2, we know that this is going to be I, right? But this is not IRMS. Like I told you, how to find out IRMS? Use the VRMS divided by the magnitude of this impedance. What is that? A squared plus B squared square root, right? So that's RMS. Okay? So what's the impedance phase angle? So this cosine theta V minus theta I, you are seeing, hey, this is the phase difference between voltage and current. This is also called the impedance phase angle. Let me know if this makes sense. Keep in mind, I hope you guys can understand this fundamentally instead of just using the equations. If you use the equations, you'll forget it like 2 days after the final exam, right? If you understand the fundamentals, it's gonna seal in your mind for a whole life. So let's look at this. Theta V minus theta I, the angle difference between voltage and current, will be the impedance phase angle. Why? So the voltage and current phase difference will be exactly the impedance phase. Why, right? Look at this. Look at this. This is an exam 2 problem, okay? So V over I, keep in mind, these are just the V and I's, complex, not VRMS. So equals what? A plus BJ, right? Or we can say it's a V angle something, right? Over I angle something equals what? A squared plus B squared. And then angle what? Arc tangent what? B over A, right? That's the impedance angle. So what's going on here? This equals what? V over I, magnitude-wise. Comes back. Because the phasor division will be a subtraction eventually. So that equals what? Make sense? Whew. So this will be this. Okay? Learn some new things. Voltage and current phase angle difference will be exactly the impedance phase angle. So this guy will be exactly the same as the impedance phase angle. Okay, so it's basically VRMS times the RMS times the cosine of the impedance phase angle. That's the conclusion. All right. So now we got a VRMS times RMS. Let's finish this up. What's the cosine? What's the cosine of the impedance phase angle? Difference. We can directly write it down. We don't really care. So AB impedance. Okay? Tell me, what's the cosine theta here? A over what? Right? So that's the cosine of the impedance impedance angle, phase angle. Put it in here. This equals what? Put this down here. So VG square over 2. A square plus B square. Compare. Let me know if that makes sense. This, are they equal? It's good to spend time here, you know, just let you guys know. It's not a waste of your time, even though I'm not directly covering the homework problems. Are they equal? Okay? That's the two methods you want to follow. That covers the first case, which is 2 in series. And you are done with it. So in the future, apply the same method. It's going to solve almost 90% of the problems. Okay? Try to derive yourself after class so you can master it. Any questions by far? Takeaways. What are the takeaways before moving forward? Spend like 40 minutes to talk about the first case. Is the tutorial due Wednesday and homework due Friday? No, you don't know.
1 day later. Tutorials on Friday.
Tutorial on Friday. Homework on Wednesday. Monday next week. Okay, cool. All right. What are the takeaways? two methods, right? What's method one? Focus on the resistor, right? If it's asking you to calculate the average power, focus on the resistor. If it's asking you to focus to do the reactive power, I'm going to cover that later. Just focus on this one, the same method. Okay, we'll do that later. No worries. So that's method one. Just focus on the device or focus on that specific component. Okay. If it's asking you to, so method two, right? Method two. Focus on the overall voltage and current, but however, you have to take that phase angle difference in consideration because there will be a phase shift between the current and voltage since you are, doing the entire circuit here instead of the single component. But now, even though this is not something written in the textbook, but let's just think about it. What average power really means? Because voltage and current, they have a phase shift. So we don't really want to directly multiply them point by point, right? So what we want to do is want to project the current to the voltage. It's not being written in the textbook, but that's how I understand it. You got a voltage, right? You got a voltage, and you have a current here, okay? And there's a difference. The difference. So how to project the current to here though? Right? That's the effective I when you want to put it in phase with the voltage. Does that make sense? So they're in the same bar, right? Instead of having a shift. So they're not in the same domain. It's very difficult to do the multiplication. So you project it to here to get this length. So that is RMS times cosine that minus that, right? And then times the VRMS is getting the average power. This is something you can understand it in a better way, I think, why we are having this term over here. But you don't have to if you don't like it. So this term is called the power factor. Power factor. Sometimes PF. Okay, some definitions. Now let's look into the second case in parallel. That'll be a very interesting problem to look into. What about this? Same concept. Okay. I'm asking you, what's the average power of the circuit? Method one. Remember, just focus on the resistor because the resistor is the only component consuming real power. Real power or average power, same thing, okay? Resistor is the only component consuming real or average power, okay? So we need to know the VRMS and RMS across this guy. Okay, so what are they? That's the peak voltage, sine wave. This exists here and here. Okay? Any difference? No, it's a wire. It's a wire. No difference. It's going to be the same Vg cosine omega t. Right? So now let's look into this resistor only. I think we'll be done after that. So Vg over this is what? VRMS. So what is IRMS of this resistor? That's it. Because that's the magnitude. Remember how to convert in between IRMS and VRMS using the magnitude of impedance. What's the magnitude of this guy? Just simply C, right? Just the resistance. Sorry, I put a C here because you will know why I have to put a C here later. But anyway, so this is the resistance, okay? So the C is the resistance, not a capacitance, keep in mind. So the resistance. So this VRMS divided by C is giving you the IRMS times what's the voltage and current phase difference of the resistor? 0, right? 1. 0, but cosine 0 is 1. So what is the result? Done. So you can just focus on the resistor. You'll be fine. What about method 2? That's a traditional method before exam 2, right? What is the overall impedance magnitude? Can you easily find it? Like C plus DJ, so it's going to be C squared plus D squared square root. Is that correct? What's the overall impedance here? It's in parallel. It's not in series. No, it's not right. It's going to confuse you a lot. That's why I'm introducing this model here. What is it? You have to do this. C times DJ parallel resistors. Use impedance as a resistor and do a parallel resistance over C plus DJ. Okay? Convert it to real and imaginary part. How do you do that? C times DJ times what? C minus DJ, and you are getting C squared plus D squared at the bottom. All right, this equals C what? Square DJ plus C D squared over C squared plus D squared. All right, so these guys have to split it into the real part and the imaginary part. So you are getting C D squared over C squared plus D squared. That's the real part. And C squared D, C squared plus D squared J. Okay, so that's the impedance of this whole thing. So method 2, focus on the whole impedance. It's still gonna work, same results. How do we do that though? Find out the VRMS, RMS, and then times the cosine theta V minus cosine I, right? Theta I. So how do we do that? So what's the voltage? So P equals VG over this. VRMS is not changing for the overall voltage. What about the current? How do we get a current? Remember, current is the VRMS divided by what? The magnitude of the impedance. This will be long. C squared plus D squared, C D squared, squared plus C squared D squared, C squared D, C squared plus D squared. Okay? Don't worry, it will eventually come to the same result. Anyway, we probably don't have time today, but next time on Wednesday we'll demonstrate that. But see here, so this is how you do, this is VRMS, this is RMS, right? So still the same method, just a parallel resistor, just have to convert it to this. Then what's the difference? There's no difference compared to the series one, right? So that's the magnitude. Cosine what? Cosine this guy, right? Okay? We'll find some time to get this done on Wednesday. But this will cover the 2 cases you will see for both tutorial and homework assignments, right? We'll solve all the problems. I'll see you on Wednesday. Okay.